Here goes nothing. Sadly, I have left my nice camera at home, so I'm stuck with this dumb smartphone, which doesn't matter to you guys since you're here. But all right, so let's get started here. I want to talk to you guys about power series, and I understand that most of you are a little bit behind the curve on that just because of COVID Cal 2, and so a lecture that's a little bit different than I might if I assumed you had a complete working of calculus 2, right? So let me just start out with the definition. The definition, what is a power series? A power series centered at Z0 is a function of the form f of z equal to the sum, k equals 0 to infinity a sub k, z minus z naught to the k power, where a sub k is a element, a sub k and z naught, these are complex constants, right? And we say, A0, A1, A2, are coefficients, of the series, of the power series. All right. And I'm going to skip past some of the theoretical results today and come back and get them in a video later, just to keep things. I'm going to carve ahead through this section, and then I'll circle back and do the theory later. All right. So this is what a power series centered at Z0 is, and there's a theorem, right? And the theorem says this: the domain of a power series centered at Z0 has three possible radii of convergence. Case number one. And let's call the radius of convergence ROC. And I'm just going to call it R for the sake of this statement, all right? So case number one, you can have R equals to 0. In this case, the domain of F, right? The domain of your power series is just equal to the set containing Z0. This is a very silly case, but it's possible, all right? The second case is that R is positive but not infinite, right? In this case, the domain of f of z is a subset possibly equal to the set of z such that the modulus of z minus z naught is less than or equal to r. Right. Saying that the radius of convergence r does not guarantee that the points on the edge converge. They may converge, they may diverge, all right? 3, infinite radius. So then the domain of the function of power series is just the whole complex plane. All right. These are the 3 possible kinds of domains. So just to give you pictures, could be that there's just a singleton Z naught, which is in the domain of the power series. The other possibility is you've got like Z naught, right? And you've got some finite radius, like that, let's say, yeah? So everything inside that disk, everything inside the open disk is necessarily giving you convergence of the series. However, maybe you only get like 1 point on the edge of the disk in the domain of the function, right? Or you might get, all kinds of things are possible, all right? All kinds of things are possible. You could include the whole disk, the whole edge as well, it's possible, all right? And then the other case, of course, is just that Z naught is here, and then everything, it's all, everything converges everywhere, right? Okay. Now, another theorem is that if f of z is equal to the sum k equals 0 to infinity of a sub k z minus z naught to the k. In other words, if f is a power series, then f prime of z exists, and it's given by term differentiation of the series. All right, so it's sum k equals 1 to infinity of k a sub k times z minus z naught to the power k minus 1. Essentially, another way of remembering that theorem is that for a power series, you can bring the derivative inside the summation and just differentiate term by term. And guess what? You can just do the same for like the higher derivative, right? Like if I have prime, what happens?
You just differentiate twice,
Right.
term by term.
Exactly. So I could leave this as k equals 0 if you like too. Well, that would be silly. I mean, I could do that though, right?
Yeah.
But
It drops though.
Yeah, for this, the first two terms would be 0, because the first one would be 0, 1 gives me 0, and so be careful with this. It's one of the things I get confused about. As I'm working with series, if you have a series where the index of the power is not just k, if the index of the power is like 2k, then you gotta be careful, because you might not have to change the summation value, because if your formula has like z to the 2k, you're going from constant to quadratic. So anyway, let me shut up about that. And this goes on, okay? So the point is, if you have a power series, it's differentiable. It's complex differentiable, all right? Are we good? Another theorem which is useful is that if, and a close cousin, by the way, to my domain theorem, but it's that if f of z1 diverges, then every z in the complex with modulus of z minus z naught greater than the modulus of z1 minus z naught likewise diverges. And here again, I'm making reference to the f of z I defined at the start of this lecture, right? So what that says is, for example, right? Here's an example. Suppose we have f of z is equal to the sum a sub k times z minus 3I to the power k equals 0 to infinity, right? And f of 1 plus 2I diverges. What does that tell us about the possible domains for the function. So we can draw a picture, right? So this guy's centered where? Z minus 3i means the center of the series is at 3i, all right? So right here, let's say. That's my Z naught, my center. And I'm just told that there's a point of divergence at 1 plus 2i, which is where? It's like here, right?
Yeah. And so that is it the circle rounding 3i of radius through like of that modulus right there, the link between 3i and 1 plus 2i?
Oh, yes, yeah, I guess that's the first question is what is that distance? I mean, so yeah, I can draw a picture here, right?
Okay.
So what's the radius of this? What's the distance?
It'd be probably 1i, so root 2, something like that.
So it's the length of minus 1 plus I, right?
Yes, that's root 2.
Square root of 2. So this is the square root of 2 to go from here to here, yeah? And so what this theorem says is that if there's a point of divergence, right, then everything outside this, everything out here, everything outside this disk diverges. Divergence of that sum, right? Now, does this mean that the domain of the power series is everything out to 1 plus 2i? It does not. We don't have enough information, actually, to say with authority what the domain of this power series is. But what we do know is it can't be bigger than the green circle.
Divergence outside the circle?
Outside the circle.
Oh.
Outside the circle. Now, one of the things I've learned studying power series over other kinds of calculus, like over in algebra, is that this theorem doesn't hold. So like all of the things we get in complex about convergence of power series tend to still hold, suitably modified over calculus over in associative algebra. But the divergence results, they fail. So this is a very powerful result, that 1 point of divergence gives you divergence outside. Right? And 1 point of convergence also gives you convergence inside.
Okay.
Not, so like, what I'm saying is, knowing that this series converges at this blue point right here, you guys look for a second. See, if I know the series converges right there, that tells me that it definitely converges on the open disk inside that. I can't say anything for sure about whether or not other points on that circle converge. But what I can say is it will converge inside. For a power series, be careful. We're going to be looking at functions which are not always representable by power series as we go on here. But for power series, that's very nice. And so I just used a phrase, a function's representable by a power series, all right? Do we have a word for that? What is that? Let me tell you about that. So I will give you examples of series here today. I just have a little bit more sort of general theoretical context here to finish. So I should come back and give you an example of each one of these, yeah? So at the start of section 5.4, I have a theorem. So this is theorem 5.4.2, which I want to state but not prove right now. I want to state the theorem and use it. All right, so here it is. Suppose f of z holomorphic. What does that mean?
Simply connect.
Holomorphic meant complex differential, right? For,
Oh man.
did I hear an oh man? For z minus z naught less than rho, okay? So on the disk of radius rho, centered at z naught, f of z is holomorphic, right? Then f of z is represented by the power series f of z equals to the sum k equals 0 to infinity a sub k z minus z naught to the k, where the coefficient is a sub k is equal to the kth derivative evaluated at z naught divided by k factorial. All right. Right. And the theorem says more. All right. But the more of the theorem I actually don't want to talk about right now, so I'm going to not talk about that just yet, okay? But this coefficient also is actually related to the integral of the function. Yeah, fine, I'll write it. I don't want to talk about this too much today, but I'll just mention here that this is also equal to 1 over 2 pi I.
It was Cauchy's integral form thing.
Integral around the circle, w minus z naught equal to r f of w over w minus z naught to the k plus 1 dw. But yeah, this is for, what was I saying? Of course, this is for k greater than or equal to 0, right? And yes, good point, Albert, that is exactly, I mean, you could have expected that because that's Cauchy's generalized integral formula, right?
Yeah, I noticed, but I don't assume.
So, that is correct. So, but there's more than this, all right? So, and this isn't in the theorem, but the definition at the start of section 5.4 says, a function f of z is analytic. So let me put the definition up here. F of z is analytic. All right, analytic on the disk of radius r centered at z naught, which here I'm saying is the open disk, so it's z such that the modulus of z minus z naught is less than r. All right, it's analytic on that if there exist if f of z is equal to the sum k equals 0 to infinity of a sub k z minus z naught to the k on dr. So what is theorem 5.42 saying? What it's really saying is just this: a holomorphic function is an analytic function. So Gamelin, I think, has confused the matter by using the word analytic for complex differentiable in the book up to this point. I'm not a fan of this. I think we should be careful to use the word analytic when we're talking about a function being representable by a series, all right? And so what this theorem says is that, hey, there's no difference between complex differentiable and representation by a series. Like, if you can do one, you can do the other, at least on an open disk, all right? So this is very nice because what is a power series but a polynomial without end, right? It's, as my colleague from Texas used to say, they're Texas-sized polynomials, right? In Texas, everything's bigger, right? But so yeah, that's kind of the big picture here in a nutshell. Is this is, and by the way, this thing right here that I wrote down in this theorem, this is the Taylor series for f. So Taylor series is this, when you plug this derivative formula right up in here, that's the Taylor series for the function. So let me recap here. If we have a function which is complex differentiable, then we can calculate its Taylor series, right? Because a complex differentiable function is an analytic function, so it's represented by its series. How do you find the series? You calculate derivatives. and plug in the center point that you want. Now the choice of the center point is not unique, so let's look at a bunch of examples that exhibit this theory, okay? Can I erase?
1 second.
Go for it.
Okay. So when we plug in AK for the derivative at a point, and then, okay, gotcha. All right.
So, so things we should have learned in calculus too, right? Well, I won't start with that. I'll start with examples. Example 1, if we had the sum, and I'm going to use n instead of k, if you don't mind, equals 0 to infinity of n factorial z to the n. All right? Then, if you look at this power series as z naught equals to 0, and the radius of convergence is 0. You can see that from like any number of different ways, like the ratio test, for example. If you look at the ratio test here, if we look at n factorial, well, n plus, say, so look at n plus 1 factorial, z to the n plus 1 divided by n factorial times z to the n, right?
Yeah.
Then this simplifies just to n plus 1 times the modulus of z, right? And that goes to infinity, because n goes to infinity. So, therefore, by ratio test, you know, f of z diverges for z not equal to 0, right? So I do need that z is not equal to 0. See, it's a get out of jail free card. If we put z equals to 0, like anytime you put z equal to just the center of the series, it makes the whole series do what? Just drop down to just the constant term. So in this case, this series converges to 1, I think, if z equal to 0. Although it kind of depends on whether you say 0 to 0 is 1. Okay, no, let's stop that. That's example. So there's example case 1, right? Example 2, we can have something like f of z equals to the sum n equals 0 to infinity of, let's say, z to the n. This is a power series. Again, has z not equal to 0. Right? What's its radius of convergence? Well, let me be a little sneaky here. What this is, if you write it out, is what? This is 1 plus z squared plus z cubed plus da da da. You should recognize this. This is the geometric series with a equals to 1 and r equals to z. So this is equal to 1 over 1 minus z by geometric series. When does that result hold? This holds for what? Modulus of z less than 1. And in fact, you can prove that if the modulus of z is equal to 1, the series diverges. So, in fact, here, the domain of f of z, it is just the open unit disk. So there's another way to look at this. There's another way to look at this problem, right? Which is what? If we look at g of z, right, equals 1 over 1 minus z. If you look at this function, is that complex differentiable?
Yeah.
It is, except for,
0. No, I mean 1, sorry.
yeah, 1, z equals 1 is a problem, right? Well, since this is a complex differentiable function, right? If we, and then we draw a picture, right? So the trouble spot here is at 1, right? So that means that if I write a power series representation for this function, and I center it at 0, then I can't get past that point of divergence. See that? I can't get past it. I'm stuck. That's as big as I'm going to be able to get is a radius 1 if I center at 0. And of course, that's what we see right here. So I think a useful exercise at this juncture is, what if we tried to find a power series for this function not centered at 1, not centered at 0, but centered somewhere else? How would we do that?
You would want it,
So you guys want to pick for me a different center other than 0 rather.
2i.
2i, okay. Let's find power series representing g of z equal to 1 over 1 minus z with z naught equal to 2i. All right? So here's how we could do that. We could say, okay, well, g prime of z is 1 over 1 minus z quantity squared. Do you see why there's no minus there? There's no minus because there's a minus from the power rule, but there's also a minus from the chain rule to compensate one another. And that happens at each order here, right? So, great. Let's see here, then what is, so to construct the Taylor series, like the most basic way of doing it, the most brute force, uninformed way of doing it is just to straight differentiate the formula and plug in the number and assemble the series. I think long term that's almost always the wrong thing to do, but for now it's a good idea. So g of, I need to plug in 2i, 1 over 1 minus 2i, right? Which I probably should take a second to simplify that. That is what? That is, so I multiply by 1 plus 2i over 1 plus 2i, what's that give me?
4 on the bottom, and yeah, I think it's 4. I think it's 4. 2 squared plus 1 squared.
2 squared plus 1
5,
squared.
definitely 5.
So we got that, all right? And so g of, g prime of 2i is going to be, anyway, so let me not get into all that. Yeah. Maybe we could spend 10 minutes doing the arithmetic here. G prime is that. You see where I'm going?
Mm-hmm.
Shouldn't have given you guys the control of the center. All right, so you see. All right, fine, great. Thus, by Taylor's theorem, and so Taylor's theorem is the one at the start of section 5.4, essentially, all right? Although, I should say, Taylor's theorem does not include the bit about the integral. That integral thing, that's complex analysis. Taylor's theorem really refers more to the real predecessor. There's no link between differentiation and integration for real functions, generally speaking. Not like that, anyway. Okay, so we have g of z is equal to, I'll write it out symbolically first here, g of 2i plus g prime of 2i z minus 2i plus 1/2 g prime prime of 2i z z minus 2I squared, and then plus 1 over 3 factorial g prime 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 of 2I, z minus 2I cubed, and so forth. So I'm just showing you how to calculate the first 3 terms, maybe 4 terms, in the power series representation of 1 over 1 minus z. And so that would be, 1 plus 2I over 5 plus 1 over 1 minus 2I quantity squared, z minus 2I. Notice the half and the 2 cancel for g prime prime, which is kind of cool. So plus 1 over 1 minus 2I cubed, z minus 2I squared. And then 1 over 1 minus 2I cubed, z minus 2I cubed, da 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 da. And there you go, that's the Taylor series for G up to cubic order, centered at 2I. Now suppose you're not content with this, you want to find the whole thing. Is there a better way to do this? There is. So when dealing with something that's like a geometric series, you should use the geometric series result. So what we got to do is, here's a trick, I'll show you the trick, all right? So, and this trick we'll need for a bunch of examples. So like this is not just a one-off, this is actually me trying to help you down the path here. 1 minus, so 1 minus z, right? Great, that's the formula. And I want to do what? I want to, centered at 2I means what? What does that mean? That means it's kind of like polynomial in z minus 2I to powers, right? So I need to create a z minus 2I. So I just do it. This is z minus 2I plus 2I, right? If you look at it, it's there, right? I added 0, yeah. And so that is 1 over 1 plus 2I minus parentheses z minus 2I. Well, see, now I messed up the 1. I messed up the 1, didn't I? Because I need, the geometric series is this. A over 1 minus r is a plus ar squared plus da 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 da, right? As long as the modulus of r is less than 1. That is what we're working with. This is the geometric series result. That's our lifeline for this problem. To not know that, to not use that, is to face the infinite despair of calculating arbitrarily many derivatives and working out the arithmetic. All right. So to make that a 1, factor it out. Just factor it out. See, this is 1 over 1 plus 2I, right? Times what? Times 1 minus z minus 2I divided by 1 plus 2I. See? It's just that. And now, recognize this is geometric. In other words, this is what the geometric series converges to, which means I can go and I can go from this side to that side for the formula. And what do I got? I've got the sum n equals 0 to infinity, all right, of a, which is 1 over 1 plus 2I, right? And I guess I can write the geometric series a few different ways. I'm going to write this. You want me to start at 0 or 1? I mean, it's up to you guys. I guess I'll start at 0.
Yeah, I don't think it.
So this would be the sum n equals 0 to infinity of AR to the n. Right? So just applying that, my A is 1 over 1 plus 2i, and my R is what?
Z minus 2i over 1 plus 2i.
Mm-hmm. So, one more step and I've got a power series. I mean, technically speaking, this isn't a power series yet, because what does a power series have to have? It has to have, to be fussy, it should have, 1 over 1 plus 2i to the n plus 1 power times z minus 2i to the n. There you go, right there. That is the power series representation of g of z centered at 2i. What's its radius of convergence?
So it's centered at z naught or 2i.
So 2i is where in this picture? 2i is
up on the
up here, right? So it's the same function, it's got the same trouble, this is the center now.
Yeah. And the radius would be from 1 to 2i.
Right, we should have it converging. I didn't do it quite right. Curses. Something like that, right? So whatever, the radius of convergence should be the distance from 2i to the trouble point. So the radius of convergence for this one, distance from 1, 2i to 1, so 2i minus 1, aka square root of 5. Look, what's the condition? What's the condition for the geometric series result to hold? When is this equality not total nonsense? It's not total nonsense when the modulus
is less than 5
of r, which is equal to the modulus of z minus 2i over 1 plus 2i is less than 1, right? But what does this condition tell us? This tells us that the modulus of z minus 2i is less than the modulus of 1 plus 2i, which, by the way, is the square root of 5. So I don't just have to argue by picture. I can explicitly show you from the calculus here that that's the radius of convergence, and that, in fact, this represents g of z on that open disk. So you mean to tell me that the radius of convergence of the power series representing a given function can change depending on what your center is? Yes, I do mean to say that. What the radius of convergence is for the power series representation of a given function is generally a complicated question. However, many functions are what are called entire. So a function is called entire if it's, see, now my watch is filming as well. Well, I guess I got about 10 minutes going by the,
Yeah, it's 11:56.
All right. I must have started late. Which means I should go doubly late, right? No. All right, so let's spend the remainder of time talking about some entire examples. So, well, going back to the theorem, I've showed you one which converges just at one point, right? We just found one that converged on an open disk, right? Now I'm going to show you examples which converge on the entire complex plane. So again, definition, if f of z is holomorphic on the entire complex plane, then f of z is entire. An entire function is one which is analytic on the entire complex plane. So examples of these. e to the z is entire. Cosh z, entire. Sinh z, entire. Cosine is entire. Sine is entire. Any polynomial is an entire function, right? These are all entire functions. What are their power series? Okay. So I'm going to write for you here the power series for each one of these centered at 0. The power series for the exponential centered at 0. And what I'm going to do for each one of these is I'm going to write both the first 3 terms, and then I'm going to write for you the summation formula. So e to the z is 1 plus z plus 1/2 z squared. I'm going to break from my convention, write the first 3 terms here. 1 over 3 factorial z cubed plus dot dot dot. So what you're looking at is the sum n equals 0 to infinity of z to the n over n factorial. That's the power series centered at 0. Cosh z? Cosh z is just the even part of the exponential. So to find cosh z, you just select the even terms from in the exponential series. That's all it is.
So 1, 1/2, 1/4 root, I mean,
1 over
factorial.
4 factorials e to the 4th, yeah. And so to get that, we can do some, let's say k equals 0 to infinity of z to the 2k over 2k factorial. In other words, think of it as n equals to 2k gives you that one. Sinh, just take the odd terms. So z plus 1 over 3 factorial, z cubed plus 1 over 5 factorial, z to the 5th, da 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 da. So that's the sum, k equals 0 to infinity, z to the 2k plus 1 over 2k plus 1 factorial. That is the power series for sinh. Now cosine and sine are the same as cosh and sinh,
With eyes.
with, not with an I, but with a -1 to the k factor.
Oh.
So it's the same thing, but it alternates. So it's 1 minus 1/2 z squared plus 1 over 4 factorial z to the 4th plus da da da, and sine is z minus 1 over 3 factorial z cubed plus 1 over 5 factorial z to the 5th plus da 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 da. So in the summation notation, sum k equals 0 to infinity minus 1 to the k over 2k plus 1. Oops. Oh, sorry. My brain was jumping ahead to sine. 2k factorial z to the 2k. And this is sum k equals 0 to infinity minus 1 to the k over 2k plus 1 factorial z to the 2k plus 1.
So, okay, so like all you do is take cosh and you chunk on a alternating -1.
You're right in that we could derive cosine and sine from the relation to the exponential.
Mm-hmm.
Many things are possible here. The larger point is the coefficients can be derived just from the direct application of Taylor's theorem. Repeated differentiation of all these functions and evaluation at 0 yields these coefficients. They're straightforward calculations that I'm not going to show you today. Let's do an example. What example was I on? 3, 4. Example 4? Maybe example 5, I forget. I'll call it example 4. So let f of z equal to, sine of 3z, find power series A
That's E5, but
with z naught equal to 0, and b is z naught equal to, fine, let's do I. And that's probably a lifetime for today. So, Okay, so centered at 0, that's easy. We just do sine of 3z is by direct substitution. And yes, you can substitute into those formulas, it works. N equals 0 to infinity. And that is not something I proved in my notes. You'd have to find a quality analysis book to find it. My bad. Minus 1 to the n, right? Over 2n plus 1 if I'm using n. So all I did was I replaced z with 3z in the formula. And I guess I changed k to n, my bad. You can do it. Use whatever letter you like. Anyway, so what we got here, again, to be fussy, it's not a power series yet, it's just a series that has no name. So this is minus 1 to the n, 3 to the 2n plus 1 divided by 2n plus 1 factorial times z to the 2n plus 1. There you go. That's the power series centered at 0 that represents this function. See, it wasn't bad, right? Now, if you use Taylor theorem directly, what would you have to do? You'd have to differentiate, evaluate at 0, and so forth. Now, B is going to require a little bit more sneakiness. So how do I see my way to what I want? What I want to do is make a z minus I appear. So I do z minus I plus I. Just add 0. And then what are you facing? You're facing the sign of 3 times z minus I plus 3I, right? But we know the adding angles formula holds for sine. I may never have proved it in here, but we could prove that's true. I should have made it a homework probably, but you're like, it's okay, we've had enough homework already. So, z minus I cosine 3I plus the cosine of 3 times z minus I sine of 3I, right? What's the cosine of 3I? That's cosh, right? Cosh 3. So what do we got? We got cosh 3, and then the sum, let's say k equals 0 to infinity, of minus 1 to the k, 3 to the k, over, excuse me, my bad. I'm gonna get into trouble here. 3 to the 2k plus 1, or 3 to 2k plus 1 here, over 2k plus 1 factorial, z minus I to the 2k plus 1. And then I think sinh of, sine of 3i, was it I sinh or is it minus I sinh? I can never remember.
That's I sinh.
I plus I sinh of 3. The sum, k equals 0 to infinity, minus 1 to the k, 3 to the, this time 2k, divided by 2k factorial, z minus I to the 2k. And there you go. That's the power series representation of line of 3z centered at I.
So why did you pull the cosine and sine out? Like, because you get a cosh term and a sinh term.
Those are numbers. Cosh of 3 and sinh of 3, those are just numbers. But I have to center.
Gotcha.
I have to center. I need z minus powers of z minus I for the power series here. Anyway.
Gotcha. Oh, I see what you're doing.
So that's it. Sorry for the miserable camera work today.